Hello dear students, I am going to discuss today the most beautiful problem of the physics, one of the beautiful problems of physics, and this is the chapter that is gravitation. Okay, the problem is like this: Griffths Capsule. It's a problem, and what actually the problem is, we are going to drop a particle from the North Pole to the South Pole, and we'll imagine that there's a tunnel which is dug from the North Pole to the South Pole. Okay, it will go downwards because of gravitational force. At the center point, the gravitational force will be equal to 0. But because of its momentum or because of its velocity, it is going to overshoot the main position. And then guess what? It's going towards the South Pole. It will retard. And finally, at the South Pole, it will come to rest. At this very point, its velocity will be equal to 0. The next what will happen is that the particle will now go in the upward direction. Again, because of gravitational force which is directed towards the center of the earth. So my dear students, this particle, what happens to the particle is that it's going to execute a beautiful simple harmonic motion. That means it is going to move from the North Pole to the South Pole, then from the South Pole to the North Pole, and endlessly it is going to repeat it again and again. Alright, now the basic question is that actually what is the time taken by the particle from going from North Pole to the South Pole and then returning back to the North Pole? That's today's assignment. So let's do it. Simply what we are going to do is that, for example, this is the particle, it is at this very point, alright, at a distance of x from the center, at a distance of x from the center, okay. Now you must know that the acceleration due to gravity inside the earth, that's equal to g multiplied by x divided by r, while x is simply the distance from the center and r, it is the radius of the earth. Alright, so this is the r, that's the radius of earth. Okay, done. The next what we are going to do is that we are going to calculate the force on this particle. Okay, obviously force will be equal to m into acceleration due to gravity inside the earth, and what that will be equal, that will be equal to mg into x divided by r. Okay, this is the force that's on the particle. There is a special property of this force. Number one is that this force is a linear function of displacement, and number second is that it's always directed towards the mean position, that's towards the center of the earth. Okay, the situation demands a simple harmonic motion, because you know that a particle will execute simple harmonic motion only if there is a net force on the particle, and that force must have two characteristic features. Number one, it must be a linear function of displacement. Number second, it must be always directed towards mean position. Both the criteria are satisfied. Congratulations, simple harmonic motion. Then we'll write down here a generalized equation for the simple harmonic motion, which we have studied in simple harmonic motion. And the beautiful equation, my dear students, is this: m into omega square multiplied by x, where m is the mass of the particle, omega, you know, it is the angular frequency of the particle, and x is simply the displacement of particle from its mean position. Now what can happen is that this x and x is going to cancel, this m and m is going to cancel. We can calculate from here what's the value of omega. Omega is equal to root of g divided by r. Okay, once you know the angular frequency, you can calculate from there what's the time period of the particle. The time period of the particle will be simply equal, that's equal to 2 pi divided by omega. That will be equal to 2 pi under root of r divided by g. Okay, so this actually is the time period of the simple pendulum. So it's not the simple pendulum, this is the time period of the particle that is executing simple harmonic motion from North Pole to South Pole and back. And this is what we call as Griffths Capsule. So dear students, when you substitute the value of the r, where r is the radius of the earth, it's exactly equal to 6.4 in 10 per 6 meters or 6,400 kilometers. You substitute the value of the acceleration due to gravity, you know that that's equal to 9.8 meter per second square. A beautiful number will come out, and that beautiful number is 84.3 minutes. This is the number that will have 84.3 minutes. Okay, now what actually it means? It means that when the particle is dropped down from the North Pole, it will go from the north to the south and then back from the south to the north, and the time taken will be exactly 84.3 minutes. Okay, so it will be exactly 84.3 minutes. Okay, so moreover, If the particle goes from the north pole to the south pole, the time taken will be exactly how much? It will be like 42 minutes. Okay, now see it is really beautiful that the particle is going from the north pole to the south pole in less than 1 hour. Okay, now there's one more thing, one more beauty in this problem, and that's here, that's for you, that's like this. And this is what we called as the nature loves symmetry. This is what we call as nature loves symmetry. What I mean by saying that is this, that this 84.3 minutes is not only the time period of a particle which goes from the north pole to the south pole, it is the time period of a near satellite. What we mean by that, for example, we have a satellite which is revolving around the earth, but it is very close to the earth. The time period of that satellite comes out to be 84.3 minutes, again 2 pi under root of r by g. Number next, weightlessness at the equator. Now, for example, imagine like this, that the earth, it spins faster and faster, such that its time period no longer remains 24 hours, but it remains 84.3 minutes. When that is the situation, then what will happen is that there will be weightlessness at the equator. All the people on the equator, they will be floating in the air because there will be no gravity at the equator. Next is this, number third, simple pendulum of infinite length. If we'll increase the length of the simple pendulum and will make it more than the radius of the earth, the time period of that simple pendulum again comes out to be 2 pi under root of r by g, beautiful, 84.3 minutes. The next is this fourth, which we have done. Okay, so it was really a great problem, one of the beautiful problems of physics. See you next time.